In this lecture, we will explore the concept of winding stress and strain in superconducting magnets. Winding stress in superconducting magnets arises primarily from the tension applied during the winding process. This tension, while necessary for maintaining the coil's structural integrity, introduces various mechanical stresses within the winding and the bobbin. The figure on the right shows a winding process of magnet with a high-temperature superconductor Rebco. In a superconducting magnet, the Lorentz force tends to push the winding outward. On the other hand, the winding tension pushes the winding inward, reducing the total displacement. Therefore, winding stress effectively reduces large tensile radial stress and peak tensile hoop stress within the winding. Further analysis shows that winding stress, combined with magnetic radial stress, significantly lowers the peak magnetic hoop stress. The figure on the left illustrates how radial stress decreases with increasing winding tension. The figure on the right shows the reduction in peak total stress when winding stress is considered. Let's explore deeper into the calculations of winding stress. We start by determining the equivalent radial stress caused by a single turn of wire. This involves considering winding tension, wire thickness, and winding radius. It can be derived from the force balance equation that was introduced when we discussed magnetic stress and strain in a previous chapter. The calculation of winding stress is a sequential process. Each turn of the wire affects the overall stress distribution, and with each layer, the effective winding diameter changes. It might not be intuitive how to calculate it, so I recommend writing a calculation code for yourself. To conclude, winding stress is one of the key factors in the design of superconducting magnets. It helps relieve peak hoop stress and contributes to compressive radial stress, which is more ideal for superconducting magnets. This winding stress can be calculated by a sequential process.